Today's experiment is the synthesis of dibenzalacetone. Alright, so this is the aldol condensation with heat, which is going to include an alpha-beta unsaturated ketone. Alright, so for this crossed aldol reaction, we're going to use acetone, which has our alpha hydrogens. We're also going to use benzaldehyde, which does not have any alpha hydrogens. And so we're going to do this in base. And so the first step is that the hydroxide will attack the alpha hydrogen on acetone, and the electrons go to the more electronegative oxygen. Now this has resonance, as I show here. The electrons come down off of the O and go on to the carbon. And so your other resonance structure has a negative carbon. A negative carbon is much more reactive than a negative oxygen, and this is the species that then attacks your benzaldehyde's carbonyl, and the electrons go to the more electronegative oxygen. And that forms this complex that has a negative oxygen, which then attacks the hydrogen off water to become the aldol product, which is a beta hydroxyketone. So any beta hydroxyketone is going to be called the aldol product. Now we are going to heat this up, and when you heat this up, your hydroxide will then come and take another one of your alpha hydrogens, form the double bond, and kick out the OH. And that forms an alpha beta unsaturated ketone. Alright, so let me label why it's called alpha and beta. So when you're talking about alpha and beta, I just put in the alpha and beta. Alright, so you're looking at the carbonyl, and the adjacent carbon is the alpha carbon, symbol for alpha, and then the next carbon over is the beta. So it's just the Greek alphabet. Alright, so that's a alpha beta unsaturated, means it has a pi bond. Over here you have your carbonyl, and then you have your alpha, your beta, and on this beta carbon you have an OH, and that's why it's called a beta hydroxy ketone. Alright, so now we're going to do the exact same thing on the other side of your acetone. And so your hydroxide again attacks the alpha hydrogen. Electrons go to the more electronegative oxygen. Alright, and so then that has resonance. I showed you the resonance the first time, so you can now do that same resonance for this one. And that same resonance is going to have the negative carbon, which is going to then attack another benzaldehyde. And so in this reaction we're going to need 2 moles of benzaldehyde for every 1 mole of acetone to form our dibenzalacetone. Electrons go to the more electronegative oxygen. That is going to attack, that negative oxygen will attack the hydrogen from water, and then you will have your OH minus attack the second alpha hydrogen, kick out the OH minus, and now you have your dibenzalacetone, which is a double alpha beta unsaturated ketone, which means it has alpha beta on this side that's unsaturated and alpha beta on this side that is unsaturated. Alright, so we are ready to do the reaction. Alright, so that is a classic mechanism. Remember, you have to do it in steps, balance every step, get the overall reaction. Alright. Alright, so we have our 125 ml Erlenmeyer flask, and to that we're going to add 2 grams of sodium hydroxide. We're going to add 10 mils of water, deionized water. We're going to add to that 10 mils of now we're going to dissolve our sodium hydroxide. I'm going to get some ice from our ice machine over here. Alright, so we're going to swirl it until we get all of the sodium hydroxide to dissolve. And when you dissolve sodium hydroxide, it gets very, very warm. And so this is a pretty hot solution here. Alright, so after the solution is cooled, we're going to add our acetone and our benzaldehyde. Alright, so I'm going to do some rapid cooling by using some ice. It still has not dissolved all of the sodium hydroxide. Alright, so we're just making our basic solution, and once we add our acetone, the acetone will react with the sodium hydroxide. I'm doing a rapid cooling while dissolving the sodium hydroxide. Alright, so we have dissolved it. It has been cooled. So all the sodium hydroxide is dissolved. And it is cooled. Alright, so now we're ready to add our benzaldehyde and our acetone. Alright, so we're going to add our 4 mils of benzaldehyde. And then we're going to add our 1.5 mils of acetone. And we swirl it. So we have a nice yellow color. Now it's an orange color. Now it's getting a darker orange color. And now it is precipitating. So it is cloudy. It is now precipitating. And this is our dibenzalacetone that is being formed right in front of our eyes. Alright, and so we just are going to collect this solid. We're going to cool it down. We want the solid to precipitate out. So again, hot solutions are going to make it dissolve. Cold solutions make your solid precipitate out. We're going to collect this on a Buchner funnel. And then we're going to recrystallize it with ethyl acetate. So remember what recrystallize means. We're going to dissolve it in a minimal amount of solvent that is boiling solvent, and then we're going to cool it down and it will precipitate out. I'm just cooling it down. The reaction was a very exothermic reaction. Set up the suction filtration. Need a little bit of cold ethanol. Some ethanol. See the solid that's in there that we're going to collect. Pretty good amount of solid that we have in there. So cooling the ethanol down. This is our cold. Alright. So when you wash it, you want to wash it with cold ethanol so it doesn't dissolve our solid. We're also going to clean it with a little bit of water as well. So I want them to be cold so it does not dissolve our product. I want to get as high a yield as possible. Right, so we have again, a good amount of solid. The reaction worked just like it was supposed to. Alright, then get our suction filtration ready. Go. From my suction filtration, can you see it over there? Okay. I put a little water on the filter paper, and so it sucked it in, and now it is ready to filter this. So as it says to wash this, the washing is also going to be the rinsing. I'm going to rinse out the flask to try to get all the solid out of here and into the flask, into the filter paper. Alright, so we're going to go with it. Alright, so I'm going to wash it out with a little bit of water. Water. Rinsed out the flask pretty well with some water. Alright, so then I'm going to wash it with some cold 95% ethanol. So now we have our product, and it is not a pure crystalline product, so that's why we're going to do a recrystallization. All right, and so we're going to use ethyl acetate. So I'm going to get a beaker for the ethyl acetate. Beaker for the ethyl acetate, and this in here and all right, so I'm going to scrape the product into this beaker, and I'm going to get a mass of the crude product, and then we're going to recrystallize it and get a mass of the purified product. All right, so this is what it looks like. It looks like a little orange, mushy solid. And I can tell that this is wet, so I'm probably getting a mass of this is going to be very misleading because it is not dry. So I'm not going to bother, I'll just get a mass of the dried and dry. All right, so you can see that in this product, you've got some of the orange product and you got some of the yellow product. So it's an interesting mixture. All right, so I have my solid in here. Again, I'm not going to weigh it because I can visibly tell that it is a wet product. All right, and so I have my ethyl acetate, and then I'm going to add small amounts of my ethyl acetate until I have dissolved so the yellow has completely dissolved, like immediately everything that was yellow dissolved. All right, so the solubility of the yellow product in our ethyl acetate is much higher than our red product, orange product. All right, so I've added all the ethyl acetate. I'm going to then heat this up and see if we can get it to dissolve. All right, so a recrystallization, remember, we have a solid. All right, so we already have a solid, just like when we started with our benzoic acid. And then we dissolved it in a solvent, and then we cooled that solvent, and then it precipitated back out into pure crystals. So this one is going to be interesting. since we have an orange product and a yellow product. Now we have two double bonds that are being formed. And so they can be formed as both of them trans, which is the usual, but you can also get a cis-trans. And if you end up with a cis-cis, that ends up to be a liquid, and that would be filtered out. But our trans, and our cis-trans product are in here. Now the orange product is the trans product. It is the major product of this reaction. Alright, now most of the solid has dissolved, not all of it. Has not all dissolved. Alright, and so when you do a recrystallization, sometimes it is very difficult to get the crystals to reform. So I'm going to concentrate this by boiling down the solvent. And you'll know you're getting close if you see that when it's boiling, this is a nice clear solution. If you see it getting cloudy, then you know that you are ready to start forming some crystals. So it has all dissolved. It now. So I'm turning the heat off. That's the thing about a hot plate. You turn it off and it's still very hot. So it looks a little cloudy right now. So I think we're going to get some solid to form. And it is forming solid right now. Great. Closer. Okay, so solid is being formed in there. as it is cooling down. And we can increase the cooling by setting it on top of some ice here. All right, and we have our nice yellow crystals. So that's a pretty good amount of crystallization. My fingers are in the way. You can see all the solid on the side. And there's lots of solid inside of that liquid. All right, so we will collect this and we will have our yellow product. And then we will determine our melting point. get a very fast crystallization. Our crystals are very, very, very small. If we would have done a slow cooling crystallization, we could have got some much nicer crystals. We're not looking for a crystal structure. So we have sufficient crystals for getting a good melting point. Alright, so I'll get capillary. Alright, we're going to do a melting point. I got some of the yellow crystals. Tap them down to the bottom. Alright, so we have sufficient yellow crystals at the bottom. Alright, turn on melt temp. Alright. Let's go to start temp. Let's go. Stop temp. Alright, so I'll give you the play-by-play by the melt temp. Alright, Digimelt. We're at 40, no melting. We're at 50, no melting. We're at 60, no melting. We're at 70, no melting. We're at 80, no melting. We're at 90, no melting. We are at 100, no melting. We're at 102, no melting. We're at 103, no melting. We're at 104, no melting. 105, we're getting some melting. 106.5 is our melting point. 106.5. So at 105 I saw a little bit of melting, and then at 106.5 it was all a liquid. Alright, so now we just have to get the mass of our product here. And the melting point for both trans is 110, and so we are definitely, we have made the both trans isomer. Alright, so let's mass the weight boat. Mass of this weight boat is 2.4193. Scrape the solid in there and get a mass. Alright, so the product is a nice yellow solid. Looks very, very pure. Looks very dry. So by the melting point, we know that we have a pure, both trans isomer of this dibenzalacetone. And if we took the NMR, we would see that we would have a large coupling constant between usually around 15 to 17 for the hydrogens being trans. You can also look in the fingerprint region of your IR to see that it is also both trans. But we have a melting point. So the melting point of one cis, one trans is 60. There was 0 melting at 60. And the melting point for both trans is 110, and we had 106.5. And it could be off a little bit because we didn't wait for it to dry. Many times we would wait, let it set a week, and make sure it was completely dry before we took the melting. Alright, so again, here is our nice yellow product that we're going to now weigh. Alright, so the mass of the weigh boat and the product, 3.2821 grams. Alright, so you have your 3.2821 grams minus your 2.4193 grams, and that is your actual yield for your dibenzalacetone. Alright, that is the end for that experiment.